First of all, I'd like to thank the invitation to be here. So, as I said, I'm going to talk about holomorphic foliations on some of the definitions and the examples. I will sometimes mention also C-infinity foliations, since they also work in the C-infinity case and not only on holomorphic case. And then I will focus on the holomorphic foliations after that. So I will start with the definition of a foliation. So let us consider M eventually smooth or a complex manifold of dimension M. Okay, and I start with the notion of a regular foliation on M of dimension M. Or if you prefer, we can also say a foliation of codimension M minus N. This is an atlas UI phi I, where the UIs constitute a cover or an open cover of M. The homeomorphisms phi I, they are defined from UI on Rn or on Cn, according to R in a smooth or complex manifold, okay, satisfying the following property. So whenever we take two open sets having non-empty intersection, the diffeomorphisms phi ij defined as phi I composed with phi j minus 1 going from phi j of the intersection into phi I of the intersection takes on the form if we take an element x and an element y, where x is on Rn and y is on R M minus N. The first component depends on y, x and y, and the second component only depends on y. Okay, so just one remark. This is my capital X. So, yes, I'm sorry. Okay, so this is my capital X. This is my small x, okay? Okay, if these phi ij's are C infinity, we'll say that the foliation is C infinity, but if these phi ij's are holomorphic, we'll say that the foliation is holomorphic, okay? So, first example. A sample example. So let us consider M manifold, smooth or complex manifold. It works in both cases. And let X be a vector field defined on M a C-infinity vector field or a holomorphic vector field. And let me assume that this vector field is non-singular at every point P on M, so it never vanishes. Okay? So to the vector field X, we can associate an ordinary differential equation that is the derivative of small x in order to t coincide is x at x. Okay? And we know from the existence theorem of differential equations that for every t0, x0 that we fix, okay, we always have a solution. That is, in the case that we are considering smooth manifolds and the t is real, it is defined in an interval AB on M, satisfying phi prime at t is x at phi prime. Okay? And we'll say that the integral curves are the image of phi. Okay, and in fact, not only the existence theorem, we also have uniqueness for the solution. So, which means that for every x that we fix, there passes a unique integral curve. Okay, so for every point x on M, there exists a unique integral curve passing through x. Okay, and the vector field here defines a foliation, a one-dimensional foliation on the manifold M. Okay, so how can we see this? We can consider the flow box theorem. That says the following. There exists a map phi from, I can say, Y to an open set of R, such that the push forward of the vector field x by phi is an horizontal vector field. Okay, so I can assume that corresponds in local coordinates by the dx1. Okay, so in this case, the integral curves corresponds to the elements x2 equal to some constant till xm equal to some constant. Okay? So if you have here our manifold M, and we consider here two open sets here, Vi and Vj, okay? On each one of these open sets, we have a map, homeomorphism, okay, such that it sends our vector field here to the horizontal vector fields. So the integral curves of these horizontal vector fields are contained in the horizontal hyperplanes. Okay, so I have here x1, x1, x2 till xm. I will denote it by y. x2 till xm. And now, from this picture, we can clearly see that phi y, phi j, so phi I composed with phi j minus 1 on x1 y is such that those horizontal hyperplanes are sent into horizontal hyperplanes. So in the second component, it only depends on y, and the first component may depend on x and y. So we have the structure of a holomorphic or smooth vector field depending on which we are considering. Here I put on the solution an interval. Here I was assuming that we are in the smooth case. If we are in the holomorphic case, I can consider here a disk centered at T0. Okay? Okay. So this is an example of a one-dimensional vector field. Before giving examples of higher dimensional, one-dimensional foliations, so before giving example of higher dimensional foliations, let me give some definitions. Okay, so I'm going to start by defining a plaque of a foliation. Okay, so let us consider a foliation. Okay, so a plaque is nothing but the preimage of these components y equal to constant on each y. Okay, so a plaque of F is a subset of M defined by phi I minus y of y equal to constant for some I. Okay. So we are defining plaques only on one of these open sets on the open cover of M. Okay. So given the plaques, we can define a relation on M. Okay. So the plaques of F define a relation on M as follows. So let us fix 2 points x and y on M. If these 2 points belong on a same open set y, they will be related if they belong to the same plaque. But if they are not, we'll say that x is related to y if there exists a sequence of plaques, okay, alpha 1 till alpha k, such that x belongs to the first plaque, y belongs to the last plaque, and 2 consecutive plaques has non-empty intersection. Sorry. Okay, so essentially we have here M, we have here x, we have here y, and we can take plaques on difference y connecting x to y. Okay, so it is clear that this relation is reflexive, is symmetric, and it is transitive. Okay, and we'll define a leaf of a foliation as a class for an equivalence class for this relation. Okay, so a leaf of a foliation F is an equivalence class of this relation tilt. Okay, and to fix notation, we'll denote by LP the leaf of F passing through the point P. Okay, so if we look to the first example, the leaves of the foliation is nothing but the integral curves of the ordinary differential equation associated to the vector field. Okay. So I'm going to think now in higher dimensional foliations, and I will introduce before that some more definitions. So again, let M be a smooth or a complex manifold. And I'm going to define a K distribution on M. Okay, so a distribution of K-planes on M, or if we prefer, a plane field of dimension K, where K is a number between 1 and M. The dimension of M was M. Okay. Is a choice, or is this choice for every point P on M of a K-plane on the tangent space of M at the point P. Okay? So if I think on this definition, there is missing a notion of regularity. Okay? So if I want to think on a notion of regularity, I can give a more formal definition of a distribution as follows. So let us take the fiber bundle given by the Grassmannian of Km into M. Okay. And we can say that a plane, a distribution of K-planes is a section of this fiber bundle. And if we define the distribution in that way, okay, the regularity of the distribution corresponds to the regularity of the fiber, of the section, okay, viewed as a map between two manifolds. Is a section sigma. Let me put here a letter. So the regularity of the distribution, I'm going to denote distribution by D, okay? It corresponds to the regularity of sigma viewed as a map between two manifolds. Okay. Sorry.
Do we consider the real tangent space or the holomorphic tangent space?
In both cases.
In both cases, the real one?
Sorry?
When we're considering a complex manifold, are we considering
We are going to look to holomorphic tangent bundles, okay? All holomorphic distributions. You can also look to C infinity, but as far as we fix a complex manifold, I will always look to holomorphic. Sorry? It can be C of order CK, C infinity, or holomorphic.
I mean, so it's a section, right? So
yes, so the section.
So the map is
yeah,
defined.
yeah. Okay. Okay, so in practice, what we can do when we look to a distribution of K-planes is the following way. So let D be a distribution of K-planes locally, and this is important, for every point P that we fix on M. Okay, there exists an open set or an open neighborhood U of P, and there exist vector fields x1, xk on P. That are tangent to M, or tangent, in fact, to the distribution, okay? And such that for every point that we fix on U, if we look to x1 at Q till xk at Q, this forms a basis for the distribution at the point Q. Okay, so this vector, we can always find, as far as you have a distribution of order k, we can always find k vector fields linearly independent everywhere on some open neighborhood of every point of the manifold. Okay? One remark that I can make here, I have mentioned this, or I have formulated the distribution in that way using vector fields. We can also formulate the distribution in terms of forms. Okay, I will return to this later. Okay, but for the moment I will keep with the vector fields. Okay, so if the distribution is holomorphic, we can always find k holomorphic vector fields satisfying this. If the distribution is just C infinity, we can find k C infinity vector fields satisfying this. Okay, so if x1, xk are C infinity or holomorphic, okay, then the distribution is C infinity or holomorphic. Just one thing, I can find, if I can find k C infinity vector fields, I cannot say that distribution is not holomorphic because I can make a bad choice for the vector fields. In fact, maybe I can find some holomorphic vector fields also satisfying this property. Okay? Okay, so just a few notions more on the distribution before considering the higher dimensional foliations. So let us take a distribution of k-planes on M, okay, where M is a small Fourier complex manifold. And let us consider vector fields x1, xk, defining this distribution, locally defining this distribution. Okay. We'll say that a subset S of M is an integral manifold of the distribution if and only if for every point P that we fix on S, the tangent space at P of S coincides the distribution at the point P, which means that it is the subspace generated by the vector fields x1 at P till xk at P. Secondly, we'll say that the distribution is integrable if and only if for every point P on M that we fix, there passes a smooth integral manifold through P. And we'll say that the distribution is involutive if for every pair of vector fields that we fix, such that these vector fields are tangent to the distribution at P, we have that the Lie bracket of them at P is also tangent to the distribution at P.
Both S and this vector fields are only local.
Yes, they are local. I don't need to put here local manifold because on each point you can look to this on every point. So on every neighborhood of this point you can have different vector fields defining it, and you still have this definition.
This S is just defined locally, right? Or you want the global integral close submanifold.
We can talk about global. So, but if you talk to global, you must have this for every point P, and on each point P you have an open set U where you have these vector fields.
The final dot on this middle point is local or is it global?
Sorry?
This integrability definition, is it local or global? I mean, S should be...
You can think on local, and then you can glue some integral manifolds after that. Okay, but as it is written, you can think on local. Okay. So the first thing to say the foliation, the distribution D, if it is integrable, okay, then we can prove that the distribution D is involutive. Okay, so this is the first remark that we can make. And I can make a sketch of the proof. So imagine that I have here the manifold M, okay? Let me consider a point P on M, okay? And I can fix here a neighborhood of this point where I have a map phi, okay? Taking us to a subset of Rm or Cm, okay? I want to prove that it is involutive, so let us fix two vector fields here defined locally on an open set U here. So at each point, I have these vector fields that are linearly independent at every point. And I can push forward these vector fields here to this manifold. So I have here phi of P. I have the push forward of these vector fields on the image of phi. Okay, so I have x, y. I associate x bar and y bar. So x bar is the push forward of x, y bar is the push forward of y. And now, since we are on Cn, Ym, I can take the Lie bracket, okay? It is well defined, it is here. And at this point here, we can, since we are just taking a chart here, we can now pull back this vector field here. And what we know is that if we take the pullback of two vector fields, or if I put here, sorry, the push forward, this is the push forward of the Lie bracket of these two vector fields. So this here simply coincides with the Lie bracket of xy, so it must be tangent to D. Okay? So assuming that it is integrable, there passes here an integral manifold. We simply take the parameterization of this manifold, and we take the push forward and then the pullback of the Lie brackets of the corresponding push forward vector fields. Okay? So what this lemma says is that we have an abstraction to integrability of a distribution. Okay? So in order to a distribution defines a foliation, we have an abstraction. And in fact, I can give an example of a distribution that is not involutive. Okay? So let us assume that x and y are vector fields on M. Okay? Let us assume also that they are linearly independent everywhere. Okay? So x, y, it induces a distribution D of two planes. Okay? And this can eventually not be integrable. The example is the following. Let's consider on R3 the following vector fields: D dx plus y d dz. Okay. The vector field y is d dy. If we take here the Lie brackets of these vector fields, it is minus d dz, that it is not tangent to the distribution. Okay, so this is an example of a distribution that it is not integrable. And so this distribution cannot define a foliation. Okay, so this is an example of a non-involutive distribution. So the distribution is not integrable, so it does not define a foliation. So in order to a distribution defines a foliation, at least the vector field has to be involutive. The distribution has to be involutive. Okay? And what Frobenius Theorem says is that, okay, this is an abstraction, but this is the unique abstraction. Okay, so we have Frobenius Theorem. So let D be a distribution of k-planes on M. What D must have to satisfy in order to say this is that D must be of class C2, okay, C2. So in the holomorphic case, this is valid. So D involutive, we have that D is integrable. Okay, which means that there exists a foliation of dimension k on M such that for every point on M that we fix, the tangent space of the leaf passing through P at the point P coincides with the distribution at P. Okay? Well, just a remark. A distribution of one planes is always integrable. Okay? Okay, it is always involutive. And in fact, if you consider the Lie bracket of two vector fields tangent to the distribution, I take one vector field F, the other vector field is a multiple of F. Okay, and so this is simply Fx applied to F times X, so it is tangent to the distribution because it is a multiple of the vector field X. Okay. So let me mention now the particular case of foliations of codimension 1. Okay, so let us take manifolds and let us consider omega a one form on M such that omega is non-singular for every point of M. This one form here always define a distribution of k-1 planes, a distribution of codimension 1 planes. And this distribution is simply defined as the kernel of the one form. Okay, so the regularity of this distribution corresponds to the regularity of the one form. So if the one form is holomorphic, the distribution is also holomorphic. Okay, but we have a sort of converse. I mean, think now that we have a distribution, okay, of codimension 1. We can always find a one form, okay, defining this distribution. So this distribution can always be seen as the kernel of this one form. However, this is well defined up to a multiplicative function. Okay, I mean that if I have two one forms, omega 1 and omega 2, defining the same distribution D, then W2 is a function times the one form F1 for some non-vanishing function F. Okay? And now, as far as we have a distribution or a foliation defined, as far as we have a distribution of codimension 1, we can easily check using this one form if this distribution is integrable or not. I mean, if the distribution defines a foliation or not. So we have the following. Let W be a one form on M of class at least C2. Okay. Let D be the distribution defined by the kernel of the one form, okay? And we have that D is integrable if and only if dW is identically 0. Okay, so some remarks here. First, dW is a three form, which means that if the dimension of the manifold M is 2, then the distribution is always integrable. Okay, a three form on a two manifold vanishes identically. Well, this is exactly what I have said here, because when we are in a manifold of dimension 2, a distribution is a line of distribution, is also a codimension 1 distribution, okay? So this is in correspondence, okay? And another remark that I should make is the condition omega d omega to be 0 does not depend on the representative of the distribution that I choose. Okay? So the condition omega d omega equal to 0 does not depend on the representative one form of D. Okay, so So in fact, if I take omega 1 as being fw, the omega 1 is the fw plus f dw. And then if we take omega 1 d omega 1, this is fw dfw plus f square w dw. This vanishes, so this is just f square w dw. Okay, so this is 0, identically 0, if and only if this is identically 0 as well. Okay, so let me make the proof of this proposition. So let me prove that it is integrable if and only if omega w dw is 0. Okay. So let us fix the manifold M. Let us look to the distribution D as being the kernel of W. Okay. Distribution of codimension 1 planes. And let us prove that D is integrable if this is 0. So let us start by taking V1, V2, V3, a triplet of vectors. Okay, and let us apply W to these vectors. At some point. Okay, so the first thing, okay, the first thing that I can say, we can assume that V1, V2, and V3 are linearly independent. Otherwise, W dw at these points would be 0. Okay. Okay. We can also assume that linear space defined by V1, V2, V3 is not contained on the distribution. Okay, why? Because if we take these applied to these vector fields, okay, those would be the sum using the permutations of W in V sigma 1, dW on V sigma 2, V sigma 3, with V sigma 2 less than V sigma 3. And if this subspace is totally contained in D, this would be 0 for every vectors that we consider there. So it would vanish. Okay, so this cannot be totally contained in the distribution. And I can say that it suffices to prove the following. We can say that W dW vanishes identically if and only if W dW at V1, V2, V3 is 0 for every triplet where V1 is not in D and the linear subspace generated by V2, V3 is contained in D. Okay? Otherwise, if we have two not in D, we can take linear combinations of them and turn into this situation. Okay, so let us take an extension, or let us extend V1, V2, V3 to vector fields that will still denote by V1, V2, V3. And such that each one of these vector fields Vi at the point P coincides with the initial vector Vi that I have fixed. Okay? And this extension can be such that V2, V3 is tangent to D. So what I have to do to prove involutive, okay, that distribution is involutive because this ensures that it is integrable, I just need to use the Cartan formula. Okay? So I have to prove that the Lie bracket V2, V3 is tangent to D. To ensure that D is involutive, which means that D is integrable. Okay, so let us use the Cartan formula. The Cartan formula for one forms says that if I calculate W dW on V2, V3, this coincides with V2 applied in W of V3 minus V3 applied in W of V2 minus W applied on the Lie bracket of V2 and V3. Since V2 and V3 are totally... Sorry? On oh yes, okay, okay, sorry.
On the left. On the left. First. Okay.
Sorry. So since we are assuming that V2 and V3 are tangent to the distribution, this is 0, okay? And so this reduces to minus W V2, V3. Okay, and now WdW on V1, V2, V3 equal to 0. This is equivalent to have W on V2, V3 equal to 0, which means that V2, V3 must be tangent to D. Okay, so tomorrow I'm going to start with the singular holomorphic foliations and defining the holonomy of a leaf, and also to talk in some particular cases where, well, the holonomy of leaf is defined along a transverse section, but we can also, in some particular cases, define a kind of global holonomy that encodes the holonomy of every leaf. So that's what I plan to do next. Okay.